and welcome to Tea Leaves Programming. Today we're programming like it's 1979. It's Haskell for Dilettantes, Part 13B, the second problem set in Haskell.mooc.fi, the excellent course, the online course by Joel Cassinan. If you are doing these exercises on the website, one thing you can do is you can actually submit your answers and get graded. And one of the cool things is that there's actually statistics for how many people have solved each exercise. And it tells quite a story. You can see that there are around, looks like 3,300 people who made it through the first problem set. And it, as you would expect, drops off steadily as you get through the course. We're at 13B right now. You can see there's between 1,200 and 1,100 people who have actually passed. But we're on 13B, so we are getting close to the end here. We've got 13, 14, 15, and 16, and then that's it. And then I don't know what I'm going to do with myself. Let's get back into set 13B, which is more monads. Now, I do always read the comments, and I actually got some really interesting feedback from one of my viewers, which is that I'm going a little too fast, in the sense of they're able to follow the individual steps, but I'm kind of skipping over some of the discussion, which is interesting because this is something I've struggled with as a video creator. I'm not sitting here burning through these exercises a mile a minute, actually. I'm sitting here and like struggling with some of them. And the problem is that watching me stare at the screen for 10 minutes is like not very interesting. So if I have 5-10 minutes of staring at something and not making progress, I generally don't put that in the video. What I do put in the video are places where I make mistakes, and then I'll cut out 10 minutes of staring at it, and then, oh, I made a mistake. That's what I did wrong. And then I put that in the video. And my thought was, well, that's interesting. That's the moment of epiphany. But if this feedback is correct, then maybe that's leaving some people behind. So set 13 has a lot of exercises. We've got how many? 9 exercises. What I'm going to try for this video is I'm going to go through and do them. But then in the editing, I'm going to pick just no more than 3, certainly, maybe even only 2. And as I go through them, I'm going to try hard to talk more than I normally do. This is a challenge. I mean, I know I seem like a talker, but it's hard to talk and concentrate at the same time, or at least I find it hard to talk and concentrate at the same time. What I'd like from you is I'd like feedback down in the comments that if in fact I've made it more boring by talking more, please tell me. If the level of detail is good, please tell me that. So the first exercise is to implement the function if-m. This is like implementing if as a monad. There's 3 operations. If the first operation is true, we run the second operation. Otherwise, we run the third operation. And they're calling out to us at the type signature here that that's a constraint, so it's only going to work with monads. We have this op bool, op then, op else. Is there any reason we couldn't run this just inside the do monad? Or should we be binding the result? All right, well, let's try it as the do monad, or in do syntax. So we have these 3 things, and all 3 of them are monads. If we bind like that, then this is now no longer an m bool. This cond is just a bool. At which point we should bind the others. We've got m bool, op then, op else. Right. Let's call it choice A, op then, choice B, op else. So now what we've done is we've taken these M of A's, whatever they are, And this is where the terminology gets weird, right? Like, we're not really stripping them out of the monad, because you can't get things out of a monad. That's literally what it means. But since we're inside the monadic context, we can kind of pretend. But if cond, then choice A, else choice B. But then all of this won't return because this is still an A and not an M of A. So we need to lift the result back into the monad. We're not allowed to return a bare A. And we can do that, I think, by just doing that. So I hope that what's happening here is clear. And this is the this is what I find to be the fundamental rhythm of the monad. As I've been working on larger and larger projects, I'm starting to get used to it. You're always doing this little dance. It's almost like sewing. You're taking your thread and you're going down into the monadic context, and maybe you're doing some stuff, and then you're coming back out the other end. Okay, and here I've already made my first mistake. So instead of just blithely going on and showing you the corrected version, let's think about what's happening. One of my tests is failing, and we could see here, you can see all my syntax errors, but you could see here, if just false, nothing, right. If condition is true, then nothing, otherwise just A, and what I'm getting for this is nothing. That's weird. This is false, so we should be getting the second branch. And in fact, if I try this with a slightly different version, you could see I get the result that I expect. I get the second branch. Why did that happen? It happened because I was oblivious about what I was doing here in do notation. I bound op then and op else to choice A and choice B, which in a monadic context, right? This binding isn't purely symbol manipulation. You can think of a monadic context as being something that you do, right? It's right there, do. It's something you run. So when I did this, op then binding to choice A, I'm running whatever that monadic context is, which means that right here, I ran the operation nothing. Nothing is a failure. And so the operation stops right here. And we return that nothing immediately, rather than going on to run the rest of these things. So actually, I can't bind either of these things in this way. And I don't really need to. I went to the trouble here of rewrapping these in a new monadic context, but actually they're already monadic. They're M of A. So I don't need to run them at all. Change these back to what they should be. I think that should work, right? That's the result we expect. Right, and now we're passing that exercise one. I hope that explanation holds water. That by doing this, you're not just assigning a variable, you're actually running the operation in a sense. Given two lists, k's and n's, find numbers I and j from k such that their sum I plus j equals n is in n's, return all such triples. So this is obviously, you might solve this with a list comprehension, and they make it clear to you in the chapter, this is something you can do. And so let's take that. But to be clear, find some 2 with a list comprehension is not the challenge, right? Because the point here is to get practice with monads. So let's do it with list comprehensions, but that's not the correct solution. Let's say that out loud. This is I plus j. No, I said x's, I meant k's. This is the problem with copy pasting code. And then this, like that. So that's the list comprehension solution. That's not what we're being asked to do. We do not want to use a list comprehension here. We want to use do notation. That's actually the task. 2k's n's equals do something. Well, can we simply start binding things? I think the magic here is that when the list is the monad, you will get loop-like behavior. And it ends up looking like a list comprehension sort of pulled out. So how do we phrase this in this world? That's going to be something like if I plus j equals n, then we're going to return the triple. So what do we do in the case where there's nothing? I think we need to return this as a list. Right, and these are isomorphic, and I think that's correct. And it kind of messes with your head because other monads don't necessarily work this way, but the list monad does. And I think that's the point of this exercise, is that this is sugar over do notation, which itself is sugar over chained binds. Ah, this one's fun. We have our result type from a previous lesson. Same functor instance used in set 12. I already pulled that up. Let's copy that over. What have we got? Implement return and bind. So return takes a value and puts it into the result monad. And our value, in this case, has to be, our monadic value has to be make result A. And the reason for that is that I don't think there's a way, well, no, it's got to be, could you take a no result or a failure and lift that into the result monad? I don't think you can, because there is no A in that situation. If there's an A, it has to be make result. I think this is as simple as let's make it more verbose. Why do I do this? This is a good question. I know I've talked about this before. Why aren't I just saying return A equals make result A? The Haskell idiom is that you would say, in the common case, return A, make result A. But these are actually in different namespaces. And so some people view this as a virtue, that because these are different namespaces, they have slightly different semantics, so very different semantics, right? One is a type and one is a concrete value. I personally, my simian brain finds it super confusing to have a name that's used at the type level and then an identical name used at the value level. I lose track. I lose track in a New York minute. So I don't always give them different names, but when I think of it, I try to. In a case like this, it's trivial, it doesn't really matter. You're probably not going to get confused by return A equals make result A, but they're in different namespaces, so I want those differences to be evident. All right, now bind's a little more interesting. We've got some value, and we've got some function. And the function goes, we can actually decompose this, right? We have, so in this case, there may not be an A because this is a result A. So we have to handle the separate cases. And if there's no result, we're just going to return that. What happened to my beautiful ligatures? That's one reason I liked using Emacs. I got ligatures. Let me see if I can get those back. Yes, I am stopping the video so that I can make it more confusing. Oh yeah, that's the stuff. That's what I'm talking about. Just gonna interrupt the video and do nothing but type ligatures all day long. So the next thing we can do is failure result, which is gonna look like, actually, let's do failure string is equal to failure string. We're just going to propagate that error through. And the last one equals function val. Clearly, I've got a problem here. What is my problem? Equations have different numbers of arguments. Of course they do, yes. Right, because here I'm also ignoring the function, and here I'm not even binding the function at all. There we go. So if you have no result, we propagate the no result. This is very similar in shape to our maybe. I think that's correct. Let's take a look. That's correct. That's correct. And now we have beautiful, beautiful Haskell ligatures that can annoy you. You know, I was thinking it's much too easy for you to understand. I have actually gotten questions about, what did you actually type there? I couldn't tell because of the ligature. This is bad for your video. And it's ironic because I've made videos criticizing people for cosplaying as mathematicians. This is my version of that. This is absolute cosplay. I just like seeing a beautifully typeset ligature. I am a hypocrite. This is bad. This is this is bad pedagogy in this video, and I apologize. I can't help it. I love a good font. I cannot say no to a beautiful ligature. You're getting ligatures. Sorry. I would love some feedback. I hope my attempt to speak more about how I'm thinking through these problems came across, and that this video had a little more context about my interior state. If you can, please leave a comment. Don't forget to like and subscribe, as the kids say nowadays. You've been watching Tea Leaves Programming. We're programming like it's 1979. Thanks for watching.